plus some A2I square, let us say. Then this A1, A2 also we know. So in this way, we know the complete model of that particular sensor. Maybe we have done very detailed experiments with that. If we know that, then also there can be uncertainties in measurement. See, we are in this phase of our course, we are trying to understand that given the characteristics of an instrument, given the things that we know about it, either from manufacturer specification or from by doing a calibration experiment, whatever it is, if we get a measurement, how can we infer from the instrument characteristics, how can we infer about the quality of that measurement, the accuracy of that measurement? How can we, possibly estimate ranges of the input variable which could have given rise to this measurement? So we are trying to understand the basic strategy for doing that, right? So we are trying to characterize that if we take one instrument and suppose it is a temperature measuring instrument, let's say a thermometer. So if we suppose we dip the thermometer into some boiling water, we dip the thermometer. Now we dip it today, we dip it tomorrow, we do 100 such experiments. Every time we are dipping that thermometer into, let's say, boiling water, we will not get exactly 100. We will not get exactly 100 degree centigrade every time. So we will get a cluster of values. If we dip it into, so we will actually get a cluster of values as measurement. It will be, hopefully, if the instrument is well made, it will be a small cluster. So we are trying to understand, we are trying to characterize this cluster and say that, first of all, when I'm saying I'm doing an experiment and I'm thinking that this is 100 degrees centigrade, actually, that is the true value of input is 100 degree. But even there, we may have some problem in the sense that suppose this liquid is, water, just let us say tap water. Suppose I've done an experiment and this tap water will have, different purity. So maybe its exact boiling point may not be maybe 100.001 degrees centigrade, that particular day's tap water boiling temperature. Maybe the depth to which we have dipped the thermometer is actually varying. So for whatever reason, the true input can vary by a small amount. So that's why there is also a small. So there can be some variation in I, even if we try to think that we are trying to measure the same input variable, there can be a small variation in I, and there can be variations in interfering and modifying inputs. So due to the effect of these three things, there can be a variation in O. So this variation is characterized due to that, and we can, as we write that, so how do we write delta O? Simple mathematics. So we write delta O by delta I into delta I plus delta O by delta II. These are the three things which are varying. Plus we write delta O by delta I Yeah, I'm sorry. I got disconnected. Are you there? Can you hear me now?
Yes, sir.
Yes, sir.
Yeah, in between I got disconnected. So coming back to the board. So up to this equation is fine. So you see, we are trying to characterize a situation where we are considering variation only due to this, and due to this. Why? Because we think that we know the true value of K, A, that is involved in the knowledge I came. This I'm assuming that we know, and there is no variation there. Oops! Why? What is happening? Oh. So are you able to hear me?
Yes, sir.
And thanks for starting the recording. It is going away. কি হচ্ছে? Yeah, the net sometimes going. I mean, something, I'm losing connection repetitively. But are you feeling? Intermittently losing connection. Let me switch over to a different network, but this is a Wi-Fi network which will not. Yeah, I'm on a different network now. Hopefully it will be stable. So I was here. Able to hear me now?
Yes, sir.
Yeah, but in between, did you feel some disturbance? I was getting disconnected intermittently. Did you feel some disturbance? Yeah. Hello. Are you hearing me?
Yes, sir.
No, but I am asking a question. That while I was losing, I lost connection about 5-6 times in the last 2 minutes. Did you feel it?
Yes, sir.
It seems you like to answer only in yes sir and no sir. So the question should be phrased like that. I'll keep that in mind.
So after you gave the equations, then the connection broke.
Right, and I was okay. Yeah, thank you. So let's go back. So this equation. So what I'm trying to say with all this is that when you are considering repeatability, then you are considering the variations in, if you are measuring, let us say, if you try to measure 100 °C temperature, let's say a number of times, suppose 50 times, you will still not get the same reading out of that instrument, because firstly there will be interfering and modifying inputs. Secondly, even if you think that it is truly 100°, there may be a slight variation in that 100°. It depends on how you are trying to ensure. For example, the atmospheric pressure on day 1 and the atmospheric pressure on day 2 may be different, and then according to physics, the boiling I mean the temperature of boiling of water will change slightly, very slightly, but still hypothetically saying. So this equation describes the output variations due to those, and well, these are unknown, right? So that's why these are random quantities. We don't know. We are not measuring delta II and IF typically. So and we may, even if we measure I, we may have uncertainties in that. So if you treat them as random variables, then we cannot calculate, of course, we cannot calculate the value of delta O. But what we are interested in knowing is, some measure of this value, something like its standard deviation, its, probability density function. If we assume it to be Gaussian, then we want to know its standard deviation. That's a measure. We may also like to know its, its range. So if we assume it to be a uniform, random variable, then we may be interested in the maximum and minimum values within which it can vary. So whatever, so if we do that, so it turns out that if these variations are independent, statistically independent, then we could, this is a standard equation of statistics, that the standard deviation of O will be given by this delta O by delta I whole mod, or when you do whole square, you don't need to do mod. So sigma square I plus delta O by delta I whole square into sigma square I plus delta O by delta IM whole square into sigma square IM. So if you have some idea about these quantities from some other sources, then you could get an idea about what is the variation in O that you expect from the instrument characteristics. Since you know the model, for example, you know what is the value of delta O by delta I square. From this model, it is clear that delta O by delta I is equal to K plus, what is the value? It is K plus, in this case, if this is the model, that is K plus A1 plus A2I plus KM IM KM IM. So you can use the mean values of these, which you think you know, to calculate the value of the sort of mean value of this. And then you can see it is fitting it to an ellipse. That's an intelligent part of the software. So this can be used. If you know the model, then you can use this term here. So this is how you can estimate the variation or the uncertainty in the output for a given instrument, and that is what is being said to being discussed in this part. So that is why statistical variations in the output of a single element with time means basically with the number of measurements, and that is called the repeatability of the instrument. But there can be, now you see, there can be a different case. Sometimes, suppose you are trying to buy an instrument. You have not yet bought one, but you are trying to buy an instrument, and you are trying to understand that whether you should buy it or not. So if you are trying to decide that, is this not coming? Now it's a oops. Okay. So now so the second case is where, so hold on, my computer is slow. So the second case is where suppose you are trying to, I went many pages below, lot of sensitivity. Yeah, we are here. So you see, this is the equation that we got. We just now got. So this is the equation that we got, that the mean value of the output will be given by this equation, while the standard deviation of the output will be given by this equation. This is what we just got. Now there is a second case. The second case is that suppose you are reading a data sheet of a sensor. Now you have not bought a single piece, so you don't know its model. But the data sheet now says, so now if you have that case, then you have some extra variations. How will you estimate? So now previously you were assuming that these values are known for a particular sensor. But now you don't know them because you are only able to see a data sheet. So if you produce, let us say, 100 resistance temperature sensors, then although they are, or let us say 100 strain gauges, then, yeah, Aniket, I'm in a class. I'll call you after class. So what I'm saying is that when you are trying to understand, so then the data sheet tells you that what is the sensitivity of, when you are producing, let us say, 100 temperature sensors or 100 strain gauges of nominal resistance 100 ohms, then of course in a batch, when you buy a particular piece, it may be 100.01 ohms or 100.1 ohms. It may be. So now if you are trying to infer you don't know what value you will get. So if you are trying to infer that, if you put that buy a temperature sensor from that batch or from that specification, and if you put it there, then what kind of variation you will get? Then you will have to additionally consider variations in these model elements also. Because what you know now is only some average values of a number of sensors coming from the batch. You are not talking about a particular sensor. So if you are talking about that situation where you only know the sort of nominal value of a batch, and you don't, and then you have this problem of tolerance. So now an individual element of that batch now has a tolerance of values, and if you want to find out that what could be the variation in the output, then you will have to consider those. I mean, where is that? Yeah. So in that case, you will have to. So now you see that when you have a batch of elements and you are only considering the mean values of the batch, then you have to consider the variations in the gains, the variations in the offsets which could occur. So this is probably not very difficult to understand, that the difference between this repeatability and the tolerance case. So in one case you think that you have calibrated for a given sensor. So you see that suppose if you are using an ammeter which is given to you and you are simply measuring it, but you may have an ammeter where there is a zero adjust mechanism. So I don't know if some of these machine lab ammeters have a zero adjust mechanism. So before taking a reading, you can actually open the ammeter and then adjust for zero, of course by eye estimation, and then connect the ammeter. So then that individual ammeter, for that individual measurement situation, you have adjusted the offset. If you don't have an adjustable zero adjust, then you have to depend on the construction parameters of that, or the specifications of that class of ammeters, and think that okay, so this particular ammeter could have an offset of maybe 20 milliamperes. But if you are able to adjust it to zero, so then you are able to probably it will be a reasonable assumption to say that the offset is zero. So this is the interpretation. So now, so you see that they have given an example here. So they are taken. This is the model of this is the actual model of a thermocouple. As I was saying, that thermocouples are nonlinear. So their output voltage depends on the difference in temperature between the measuring junction and the ambient or the reference junction. It happens very often for accurate measurements. We keep the ambient try to keep it at a fixed temperature. Like we can try to keep it in. We will keep it in ice baths so that it will be nearly 0 degrees centigrade. But sometimes keeping an ice bath is really a cumbersome thing to make measurements. So suppose we leave it to the ambient. Just simply leave the second junction open. We just connect it to the circuit and leave it in the ambient situation. Then the ambient temperature when you are measuring could vary. So now you see that so then that will have some impact. So and they are giving some values. So they're saying that the mean value of A0 bar is this, mean value of A1 bar is this. This is for a particular type of thermocouple. There are various types of thermocouples. And you can see that the nonlinearity is because the parameter is mostly linear. At least when the temperature difference is not, let us say this 10 to the power minus 6. So if the temperature difference, if you are not going into about over 100 degrees centigrade, if you are, let's say, a 20 degrees centigrade difference, T minus TA is 20, then you will see that this term is really negligibly small in amplitude. If this is 20, then this term will be very high. But then this, if it is 150, then this term may be comparable with this. So there will be some nonlinearity, right? So and they are saying that, so they are talking about standard deviations of sigma A0 and sigma A1 and sigma A2. What does it mean? That there are, when you make the thermocouples, you make the wires of certain materials, and there could be material variations, and therefore these Seebeck coefficients of thermocouple EMF could vary. And they are you can see that they are only considering the variation in this, say A0, and they are saying that the variation in A1 and variation in A2 are actually negligible. While they are assuming that the ambient temperature could really vary by about 20 degrees centigrade. So it's they're talking of a Western country. So typically in a Gaussian distribution, you can say that the temperature stays within plus minus 3 sigma 99% of the time. So they're saying that the ambient temperature, the mean value is 10 degree, and the ambient temperature can vary from minus 10 to plus 30. Almost always it is within that. So that's why they have chosen sigma TA to be 6.7. Now, so now using this, so you can calculate delta E by delta A naught, and so there are only two things varying here. One is A naught, not A naught. What is varying here? Delta E by delta A. This is wrong. Delta E. This should have been A1, right? So delta E by 1 second. Delta E by delta A naught. Oh yeah. Delta E by delta A naught. Correct. So delta E by delta A naught is of course 1. So is A naught varying? But is because A naught is varying. So therefore they're consider delta A naught. There is some variation in A naught, and there is some variation in TA. So delta E by delta TA they are considering, and from this expression using mean values they have calculated this to be this value. So now the mean value of the output can be at any given temperature can be easily calculated using all mean values, and the standard deviation of this output can be considered from this value. So this is, so you see now they are, so this is exactly the same thing they have calculated for a, you see what happens is that in a typical measurement system, right? So this is a thermocouple. So the thermocouple is taking temperature and producing a small millivolt output. Now, what will you do with this millivolt output? Probably this temperature is being produced at some point, maybe in some welding, something is being welded, and you want to know what is the temperature around the welding or something like that. Just arbitrarily saying. So the millivolt voltage is there, right? So you have to now convert it and take this. First of all, you have to make the signal stronger, and you have to make it to, and you have to build it to, get it to a place where maybe which is slightly far away. So in such situations, you have a millivolt to current temperature transmitter. So you take the thermocouple and you connect it to this millivolt to current temperature transmitter. So it jacks up the millivolt to volts and then converts the voltage to current. We know enough electronics and op amps to know how to convert a voltage to current. And then it will probably transmit it to a set of wires to a point where it can be displayed maybe on a computer screen. So now, what they are trying to, and we'll do this maybe in the next class, not in this class, that this is one part of the measurement system. I mean, the thermocouple is one part of the measurement system, and the thermocouple output is now connected to a millivolt to current transmitter, which is another part of the measurement system. And then this transmitter may be interfaced to a computer using some AD converter, and so that may be the last part of the measurement system. So if we have, so this is another part of the measurement system, and we can do exactly a similar analysis for that. So the characteristic for the current to millivolt converter is this. This is the model for the current to millivolt converter. What do we see here? That this is the actual input, which is the millivolts, and that is, so suppose the converter is giving 4 to 20 milliampere for 2.02 to 6.13 millivolts input. I don't know how they have chosen this 2.02 to 6.13. Probably they represent certain temperatures here. Probably because these values seem to be well chosen. So they have, anyway, whatever it is, we have 4 to 20 milliampere is very standard range. Standard current transmission range is 4 to 20 milliampere. Every current converter, every current transmitter will have its output in this range. So from there you can, and this delta TA is actually, you can see that this delta TA is again acting both as this is a modifying input because it is Km, Im, I, and this is also acting as an interfering input. So the same temperature, ambient temperature, is acting for the current transmitter as interfering and modifying. So you can do the same analysis again. So now you see, initially you started with this and you have calculated the possible variations in millivolts for a given temperature. Now if you connect that thermocouple to a current transmitter, then using now you do the same analysis, and now you can see you can find out that if this is the variation in the millivolt output of the transmitter, then millivolt input of the transmitter, then what is the output in the ampere of the milliampere output of the current transmitter? What will be the standard deviation? That will also have an answer. So that you can calculate exactly the same way. So you are again using these delta I by delta TA quantities, and you are using this sigma square delta T, and so you see these values are given. So I mean sigma delta TA is actually given as where is sigma delta TA? Sigma delta TA is 6.7 as given previously. So that is being used, and sigma square A, that is also something which is given. What is sigma A is 0.14, and so you can now calculate the uncertainty in the output. So in this way, since instrumentation systems are typically, so a very valid question is, going to the blackboard again, taking a new blackboard. So a very valid question is now, if I have a measurement system where there is a sensor, there is a, so here you have the actual measurand, and here you have the sensor sensing. Here you have the signal conditioning, our block diagram that we considered. And here we have signal processing. So each of these, so you see it is in, you can call this as the input I, and then this is the first block, so we can call it O1, which becomes I1 of, this is I1 of the next block. Rather, we can call it I2, suppose we call this I1. And then we have O2, which is the output of the second block, which becomes I3. And then we have O3, which is the, let's say, the final output. So we can, block by block, we can do the same analysis, and we can take, once we calculate sigma square O1, we can put it as sigma square I2, then calculate sigma square O2 and then put it as sigma square I3. In this way, we can calculate what will be the uncertainty of the whole measurement system. So in the measurement system of individual blocks, and if we know the characteristics of these blocks, then we can put these characteristics together and calculate the uncertainty in measurement that we can expect from the whole system. So this is a very interesting thing. We'll come to calibration later, but this is exactly what is done in the next chapter. So we are crossing the next chapter, crossing over to the next chapter, and in the next chapter we have so we'll do the calibration part later. So we are coming to chapter 3. There are one of the reasons why I like this book so much is because of the problems that he has given. So this has a very nice collection of problems. You must try to solve these problems. Although we will give you some assignment sheet, but if you will find a lot of very nice problems given here where you can sort of test your understanding. So we come to, now we have this situation where we have a number of blocks. So this is what I was saying, that you have a number of blocks and each block has its own characteristics. Here it is only given as it's a very simple model is used, but it need not be simple. So in this case, so for example, this is a case. So you have a thermocouple. Previously we were talking about a millivolt to current transmitter. That will be required if you want to really convert it to current, and that is generally required when you try to transmit a value over some physical distance, several tens of meters. But if you are not interested in that, if you are making a local measurement, then there's no need to convert to current. We'll later see that a voltage signal cannot be transmitted over a long distance, particularly a small analog voltage signal can never be, because it is very susceptible to noise. Even an amplified voltage signal will also be very susceptible to noise if it is transmitted 1 feet, 2 feet, 1 meter is fine. But if you want to transmit a signal to, let us say, 10-15 meters, then it is not advisable to transmit it as a voltage. It will be very susceptible to noise, particularly in an industrial environment. So, but in this case, what they are showing is it's a very simple case. So they are taking a simple case that, suppose we have a thermocouple. So this is a thermocouple which has a sensitivity 40 microvolts per degree centigrade. So what does it mean? That if the difference between the measuring junction and the reference junction is 1 degree centigrade, if it changes by 1 degree centigrade, then the output voltage between the measuring and reference junction changes by 40 microvolts. 40 microvolts. So you can see it's a very small signal. And then this is multiplied by an amplifier whose gain is 1000. So then it becomes 40 millivolts per degree centigrade. And then you see that there's an indicator. So the indicator takes this voltage and converts it to a finally, any indicating instrument finally has a gain of 1 because it is supposed to indicate the value. If it is being used in a control system, then it may not have a gain of 1. But if it is an indicating instrument, then finally the gain between the true temperature and the measured temperature is supposed to be 1, because the measured temperature is supposed to indicate the true temperature only. So therefore you can see that that's happening. This 40 microvolt into 1000 is 40 millivolts. So 40 millivolts into 25 is 1. So now if you have such a system, so now you see that you can calculate this is what I was saying, that if you have several blocks, then you can have I1 bar is equal to I bar, which is the assumed value of the input. And then from I1 bar, you can calculate O1 bar, which is using the known values of this block 1. Known values, or the data sheet values of block 1, you can get O1 bar. Once you get O1 bar, you can treat it as I2 bar because O1 is nothing, because I2 is nothing but O1, and then use I2 bar as O1 bar and then put in this expression to get O2 bar and so on. So you can do it for any number of blocks to get the mean value of the final output. That's very easy to understand. And similarly, now you can calculate the standard deviations, as we have seen that we can calculate the sigma square O1, and then sigma square O1 we can treat as sigma square I2, and then take these again and calculate sigma square O2, and in this way we can finally reach sigma square O. So this probably looks a bit abstract, and you are not able to, probably it could happen that you are not able to appreciate why we are harping about it. But if you see an example now, so that really clarifies matters. So they've given an example now. So you see that they have this situation. So what is the situation? The situation is that they are measuring temperature, but not using thermocouple, using a platinum resistance temperature detector, which is a resistance. And there is a resistance to current transmitter. Again, you are using a current transmitter, and then finally there is a recorder. So we want to know that if we know the characteristic of the temperature detector and the characteristic of the current transmitter and the characteristic of the recorder, how can we find the characteristics of the final measurement, right? So exactly the same thing. So this is what they are doing. So see the platinum resistance value changes with temperature in a nonlinear fashion, and that it's always true, although we learned in our first year only the first 2 terms. But when the temperature is high, difference is high, then the term beta comes into play. Again, beta is small, as you can see. So, and there are, now you are seeing that if you buy let us say a platinum resistance thermometer from a manufacturer, suppose you are trying to design this system and you are trying to understand, suppose you are trying to understand that whether a given platinum resistance thermometer manufacturer, which is giving you a slightly because it's platinum, so whether it's giving you a slightly cheap sensor, but then the sensor has some specifications. You are trying to understand that whether you should buy from that particular manufacturer, and because it's cheap, if you buy it, then and if you connect it into this sort of system, then what kind of quality of measurement you will have. Suppose you are trying to understand that. So then this is a procedure to be able to estimate that. So this is a mean value, but the manufacturer has stated that there could be variation because of the purity of platinum that is being offered. There could be a variation in alpha and beta. The mean values are these, but they are saying that in this case they are of course saying that alpha and beta does not change, but this R0 value, the R0 value 100 value, this can change. So they are saying that it can vary from this, again, you know, applying the plus minus 3 sigma rule. It looks like it can vary, you know, roughly between 99.9 and 100.1. 3 sigma is what? 3 sigma is 12.99 into 10 to the power minus 2, which is like 0.1. So plus minus 0.1 ohm variation may be there in R0. That is the grade of the thermometer that you are being offered at a given price. So now if this exists, then the resistance variation due to the variation in R0 in a thermometer could give you, will be so overall standard deviation will be sigma square RT at T equal to 117 degrees centigrade, right? So we are trying to see what is peculiar about 100 degrees, 117 degrees centigrade. I cannot imagine, but there is some range of measurements that it is considering, and probably 117 is around in the middle of the range. So between 100 and 130 degrees centigrade, this measurement is supposed to be made. This instrument for some reason is being designed for variation between 100 and 130 degrees centigrade. So they have taken a point 117. Why 117? Why not 115? I don't know. So anyway, so at 115, due to this variation of sigma square R0, you could have a variation of sigma square RT. And then if you connect it to this, you have again purchased, let us say, some current transmitter, which again has some parameters. Then you can actually find out what will be for the same variation in sigma square at 117 degree, for variation in R0 and for variation in ambient temperature and for variation in some offset, what could be the current variations? And then if the current variation you see that, then it's going to a recorder. So in a recorder, there is the recorder is, suppose you are taking it into a computer. So in a computer, you don't have any variation of this K and A, because it's just programmed as a number, right? So that's why they have said that sigma K is 0.0 and sigma A is 0. Oh, sigma A they are adding because it's not a computer. It's a recorder. So they are saying that there could be some variation in the offset for some reason. I don't know exactly why, but that's unimportant. So you see that finally, at the recorded temperature, this is going to be the overall standard deviation. So I don't know whether they have calculated values, but so you can now understand that if you buy from that platinum resistance manufacturer, and if you buy from that recorder and you put together and make it an instrument, what kind of quality of measurement you are going to have in that instrument, that you can estimate. We will solve problems on these, but our time is up. So therefore, we will stop today. And sorry, I did not stop in between. I was kind of moving from one this thing to another. I'll stop presenting. So we are at the end of the class, looking at a long weekend. So our future is bright. So do you have anything to say? Probably not. Plunge into the weekend. Yeah? कुछ बोलो भाई. Pratyush is, what do you call this picture? This picture is called what? Your picture is very jolly. So Pratyush?
Yes, sir. Yes, sir.
How do you feel right now?
It's just normal, sir.
Not well?
No, sir. It's normal. Like
normal? I am not normal. Of course, I now have a meeting with the director, who is my boss.
Oh, yeah.
So
I was talking about the weekends, sir, long weekends.
Oh, you were talking about that.
Yes.
So how are you guys? I mean, situations. I mean, you guys are going out in the weekend. Where do you live, Pratyush?
In Bihar. Sir.
अरे बिहार क्या?
We
Say,
go outside like.
I mean, I live in the northern hemisphere. Don't talk like that.
Oh, okay. Sorry. Sir.
What do you mean Bihar? Where in Bihar?
In Moti, in East Champaran.
East Champaran.
Yeah.
Okay. So is it a subdivisional town or divisional town?
Yes,
Champaran,
yes, sir.
East Champaran is, I guess, a district of Bihar.
Yeah, it's a district. Sir.
So are you in the district town?
No, sir. In the outside area of that district.
Right.
Yeah.
So उधर क्या होता है? फुटबॉल होता है? No.
No, sir.
No game है. COVID.
No.
But बिहार में COVID इतना खास कुछ नहीं है. Those
But
who want to
मेरे
leave,
आसपास
I'm
नहीं है,
doing
sir.
small talk. If you have a question, you can ask. If you don't have a question and if you're really in a hurry to leave, you can leave. I'm just chatting with Pratyush for 2 minutes. Well, I'm feeling like it. Others, if Pratyush.
Yes, sir. But no one is with me to play with. Like.
क्यों? ना अच्छा play से शायद होता नहीं है because
Yes.
social distancing and all.
Yes.
So what do you do? I mean,
just sitting idle or just on laptop. That's it.
again laptop. Of course,
Watching something, sir.
I have
YouTube or
started
something.
seeing. I'm not a good. I mean, much of a movie this thing, but I started sort of seeing Netflix. I am seeing the Good Doctor serial, which is nice.
Yes, sir. That's nice. The Good Doctor.
So और कुछ बोला? Yeah, it really feels like talking. I don't know how you feel, but I feel like talking.
Yes, sir. Same.
Jiruwala Nuruddin. What's your name? Should we call you Jiruwala?
No, sir. It's Nuruddin.
Yes, Nuruddin. Okay, Nuruddin. Where are you from?
Sir, I'm from Bhavnagar, Gujarat.
Bhavnagar, Gujarat. I mean, I went to where there is this Pipawa. Do you know Pipawa?
No, sir. Is that a place or?
You haven't heard of Pipawa?
I mean, I'm not sure.
You are not sure whether you heard of it. Okay, so Pipawa is a place where there is a Reliance shipbuilding factory.
Okay.
So, and I went there, and can you believe it that in and around Pipawa, wild lion groups roam around? People just, nicely chatting on the road, and other, 200 meters into the field, 6 lionesses are sitting. I've seen it with my own eyes. Wild lionesses. But I mean, apparently they don't attack people. In Gujarat, this is not the Gir forest. So Nuruddin, did you know about it?
No, sir. I actually heard the name Pipawa for the first time.
Wow. But I have seen there. So I have been there. I have seen. I mean, I have great luck for wildlife. But there were 2 cars, and the second car in front of that car, 2 lionesses crossed. So they just hang around. They just move around. Sometimes there is a small forest nearby, but people are living. It's like a road. People are khatiya laga ke baitha hai, and there are lions in the vicinity. My goodness. In Gujarat. Anyway, anybody has something interesting to say? Shreya?
Hello, sir.
Say something. Don't say something.
Nothing. If you can tell us when the college will open.
That's right. Arey bhai. ये ना खतरनाक चीज है. No answer to this question. अभी 500 student. Again.
We were in hope that it will be open by January, but now I think that we'll be graduated online only.
Nah, may not be. Why do you think that? Why do you think that?
Because no one is coming to campus, right? Only resource constrained students.
No, I don't know how you think. Look at it. Yeah. So I understand that, but you, see, I am a die-hard optimist. I mean, my family members say you are beyond redemption. तुम्हारा कुछ sense नहीं है. But I am an optimist. Why do you think that it may happen? See, people in this COVID, I have understood that people are sometimes some people are so, conservative. They're thinking, hey, ये हो सकता है, वो हो सकता है. I mean, my own close friends. In Kharagpur, we don't meet. Can you believe that? I don't go to anybody's house. Why? So I don't think so. You see this. Every day for the last 10 days I am watching. It's not that much rising. Well, in the campus there have been in the last 10 days there have been some cases in the campus. Last RB, what is that called? BRH. B.R. Ambedkar Hall में there were 5-6 cases, but they are being dealt with. Actually, the problem is, the problem is very. It's this thing. I mean, why people get afraid is that, if one, the problem is that it's not statistical.
Yeah, even if one person gets.
Even if one IIT student, something happens, it will be a crazy chaos.
Yes.
So that's what people are scared of.
Sir, in the campus, is vaccination going on?
Yeah, so we did one round of vaccination was done. Now the second round there is a talk of So my first vaccine was in campus, but then there was a private organized vaccination for students, etc. The research scholars who are here. That happened. Another such vaccination is being organized for people here. But if you go outside they are not offering. I think they are offering only second dose first. If you go to let's say if you go to a Prem Bayar hospital or somewhere. So, but if you are willing to spend money, at least I know of the Calcutta situation. If you are willing to spend 800 rupees, you can get vaccinated in a moment. Not a problem.
Yes, second, I'm living in Maharashtra, like second dose, people are not, earlier it used to be that they were in high demand. Right now, the slots are going empty and stuff.
क्यों? ये देखो, लोग को भी देखो, लोग का क्या सोचने का ढंग है. Why is second dose going vacant?
I don't know, sir. I think it is some logistical issue for first and second dose.
क्या logistic? What logistic is?
I don't know, sir. In CoWIN it is showing a lot of empty slots. Earlier, like
CoWIN. Empty slots for what? This
second dose of vaccination.
Second dose of Covishield.
Yes, sir.
पता नहीं. I don't know whether people, because in Covishield between first dose, second dose, lot of gap, na. So, but why that should not be a question. I don't know. So people look at America. There people don't want to get vaccine, right?
Yeah.
They're supposed to be very reasonable and scientific minded and all that, right? So people are off money, and especially in these type of situations, you will really understand how people can think. Educated 21st century people, how they think. You will see. So those things are coming, but I am very hopeful. I am thinking that this is the last online semester.
Yes, sir. Vaccine is like the hope for us. Like they will call fully vaccinated.
कितना लोग तुम लोग लिया है क्या वैक्सीन? Anybody who has not taken? Abhinav, have you taken vaccine?
Hello.
Yeah, have you taken vaccine?
Sir, first dose I have taken. Second dose is due it in September.
Wow. Akshit, Ishan, Shreya, have you taken vaccine?
Yes, both doses.
Both doses. Wow, good. Yeah, लेना है. See, as such, I am coming to office both halves. घर में बैठ के क्या होगा भाई? But anyway, precaution लेना है. That is true. ठीक है, चलो, अच्छा लगा बात करके. That's good. But yeah, so we'll next class on Monday. Yeah, have a great weekend. मजा करना है. मैंने we have to keep it मैंने till it holds. मैंने we have to keep ourselves. मैंने ये doomsday thinking is actually no good at all. क्या कुछ नहीं हो रहा है, but it is affecting people also. Some people. I mean, you can do many things. For example, I discover I'm really enjoying this Good Doctor serial. Wonderful. Chalo, bye bye. See you on Monday. Okay.